Welcome back. In this video, we will continue with Introduction to Processing Units. The contents of this video are difference between microprocessor and microcontroller, assembly programming, internal working of computers, development systems for microprocessor and microcontroller. So going to difference between microprocessor and microcontroller, a microprocessor contains no RAM, no ROM, and no I/O ports on chip. Hence, it is called as general purpose microprocessor. The disadvantage of microprocessor is the addition of external memory, it can be ROM or RAM, and I/O ports makes the system bulkier and much more expensive. The advantage of microprocessor is flexibility. The designer can decide on the amount of RAM or ROM input output ports needed to fit the task that is to be executed. So the block diagram of a microprocessor goes like this. It has a central processing unit. From central processing unit, we have address bus and data bus running, A bus and D bus. And all other devices that's required, it can be RAM, it can be ROM, I/O, input output port, timer, serial communication port, all are interfaced to the CPU externally. This makes a microprocessor unit. Going on to a microcontroller, it has a CPU, that is a microprocessor, and also fixed amount of memory, input output ports, and a timer all on a single chip. In other words, I can say it is a processor with memory, that is RAM, ROM, input output ports, and timer all embedded together on a single chip. The designer cannot add any external memory, input output port, or timer to it. Fixed amount of on-chip ROM or RAM and number of I/O ports in this microcontroller makes it suitable for many applications in which cost and space are critical. So when I have to draw the block diagram of a microcontroller, I can say it has a CPU, RAM, ROM, I/O port, timer, serial communication port, all built on a single chip. So microprocessor and microcontroller are widely used in embedded system products. An embedded system product uses a microprocessor or a microcontroller to do only one task. Say, for example, a printer. So in an embedded system, there is only one application software that is typically burned into ROM. Whereas a personal computer can perform varieties of tasks because it has RAM memory and an operating system that loads the application software into the RAM and allows CPU to run. Then what is the criteria for choosing a microprocessor or a microcontroller? There are many criteria. Availability of software development tools like compilers, assemblers, debuggers. It can be packaging, whether we need dual inline package or quad flat package. The amount of RAM or ROM required, the number of I/O ports and the timers required, the power consumption, speed, cost per unit, and to check whether 8-bit, 16-bit, or 32-bit microprocessor or microcontroller is best for an application. So based on all these, we can go in for a microprocessor or a microcontroller. Going to assembly programming. CPU can work only in binary, that is zeros and ones. It can do so at a very high speed. But as a programmer, if we have to give some instructions in terms of binary, it is very tedious to deal with ones and zeros. So in order to program the computer, a programmer needs some easier method. So zeros and ones is called machine level language programming. In the early days of computer programmers, the programmers were used to code all the programs in machine level language. Although hexadecimal system was used as because it is more efficient to represent binary numbers in hexadecimal, the process of working in machine code was still a cumbersome. So eventually, they thought of developing languages and they came out with assembly level language programs. It, in assembly level language programs, mnemonics are used. The mnemonics are used for the machine code instructions, and along with this, other features made programming faster and less prone to errors. So then we have assembly level language programming called as ALP, stands for Assembly Language Programs. It must be translated to machine code and it is done by a program called an assembler. Assembly language is called low-level language as it directly deals with the internal structure of the CPU. So assembly program will be something like this. When I say move R1, R0, it means to say we are trying to move the contents of R0 to R1 register. R0 is called as source register, R1 is called as destination register. So move is the mnemonic used. Similarly, if I say add R1, R0, again it depends upon the type of ALP that we are using. Add R1, R0. I mean to say the contents of R0 and R1 are added together and the result is stored in R1. This is called as destination register. This is called as source register. In this instruction, R0 is a source register. R1 acts as both destination register as well as source register. But what is the drawback? To program an assembly level language, the programmer must know all the registers in the CPU and the size of each and other details. Inner details are required. So nowadays, many different programming languages like C, C++, Java, and others can be used. These languages are called as high-level languages because programmer does not have to does not have to know what is going on internally. He may not have to worry about the internal details of the CPU. This, these high-level languages are translated into machine code by a program called as compiler. Going to structure of assembly language, an ALP, that is assembly language program, consists of series of lines of assembly language instructions and directives. So ALP will have directives, instructions. An instruction consists of mnemonics and optionally followed by one or two operands. So it is like this: mnemonics, mnemonic followed by operands. So instructions are given to the CPU to execute. Directives are given to the assemblers. So directives will not generate any machine level language code. Only instructions are converted to machine level language. So an ALP consists of assembly level language instructions and directives. So syntax can be written like this: label, mnemonic, operands, whatever I have written in square brackets are all optional. So label is a label given to the particular instruction, that is optional. Then the mnemonic, then followed by one or two operands. Again, operands are not compulsory, they are optional. So written it in square brackets, then followed by commands. Now let us study the internal working of computer. When set of instructions are given to the CPU. So let me say I will have to perform some task like this. I will have to move R0 contents into R1, then add to R1 value of 40H, then again add a value of 20H to R1, and finally halt the process. So these are the set of instructions that I want to execute. I have taken a random example, and let me assume that data bus is 8-bit in size and address bus is 16-bit in size. And also I will assume that CPU can access memory from address 0000 to FFFF. This is all in hexa, so hex. And let me assume that when move instruction is converted to machine level language, if the binary equivalent, or in other words, I write it in hexadecimal, the hexadecimal equivalent is B0H. When add instruction is converted to machine level language, let the instruction be converted as some C0H. Let halt have an equivalent of some D0H. And hex. So when this program is stored in memory, it will be stored like this. So code will be B0H. What does this code indicate? This code indicates that the content of R0 will be moved to R1 register. Then C0H. C0H indicates that some content, some immediate value has to be added to R1. Then this instruction will be followed by a code by the data. The data is 40H. Then again we have add instruction, binary equivalent, or in hexadecimal it is C0H. C0H tells that some immediate value is to be added to R1. So C0H followed by a value 20H. And finally we have alt instruction whose hexadecimal equivalent is D0H. How will this be stored in memory? Let me assume that this program is stored in some random location in my memory. Let it start from 1800. So in 1800, I will have B0H. In 1801, I will have C0H. In 1802 location, I will have 40H. In 1803, I will have C0H. 1804, I will have 20H. In 1805, I will have D0H. So what are the actions performed by the CPU? The first action will be program counter will be loaded by the instruction from loaded by the address of the instruction which is to be executed. So the first instruction is stored in 1800. So program counter will have an address of 1800. CPU is now ready for execution. The CPU will put this address, that is 1800H, on the address bus. Memory circuit will find for this location. CPU will now activate the read signal. So this will cause the contents of the memory location, that is 1800H. What is the content in 1800H? It is B0H. So B0 will be put on to the data bus and it will be brought into the CPU. So data bus is now having a value of B0H. When this process is being done, PC will be automatically incremented by 1 and now PC will hold 1801H. So when this value is brought into the CPU, CPU will decode the instruction B0H using instruction decoder dictionary and it will find out that it is move instruction from R0 into R1. So CPU will command the controller circuitry to do the required operation. Now the program counter is 1801H. CPU will put out this address again on the address bus to fetch the next instruction. Memory circuit will find the address and in this memory address in 1801 we have contents C0H. So C0H is fetched from the memory location, that is 1801, and decoding the value of C0H, the CPU will understand that addition of immediate value into R1 has to be performed. Meanwhile, PC would have been incremented to 1802H. So when CPU realizes that it is addition operation to R1 register, it will again fetch the value of 40H from the memory, and it will be brought into the CPU as explained before, and the addition operation will be carried out. Meanwhile, PC would have been incremented to 1803H. Again, CPU will put out this address, memory circuit will find out this address, and it will bring the C0H into the CPU. Then this instruction is brought into the CPU. Again, it will be decoded. Again, the CPU will understand that it is addition operation, addition of some immediate content to R1 register. So again, meanwhile, PC would have been incremented to 1804H. So again, the value of 20H will be brought into the CPU and it will be added with the contents of R1. So the process will repeat if you have n number of instructions. And finally, when the halt instruction, the hexadecimal equivalent is D0H is encountered, the CPU will finally halt. If the halt is not provided, CPU will continue updating the PC and fetching the next instructions. So in order to stop the CPU from execution, they will have to compulsorily provide halt instruction. Make a note, if a CPU is decoded, if the CPU decodes an instruction and if the CPU understands what instruction is to be performed, it acts accordingly. Say for example, instead of this 20H, you say you have C0H itself. So when this instruction could have been decoded, the CPU will understand that it is addition operation of an immediate value into R1. So whatever value is fetched next will be added. Again, C0H will not be considered as some opcode or some mnemonic. So the way the CPU will react to the instructions. Moving on to development systems for microprocessor and microcontrollers. Developing a microprocessor or a microcontroller based application requires a hardware platform with microprocessor or a controller as a central unit. The platform that is selected must allow the user to load various programs into the processor for testing various interfaces. Such requirement for a hardware platform has led to the development of so many tools. Let's consider few tools here. The first one is starter boards. So they are single board system with one microcontroller as the CPU. They are supplied by the microcontroller manufacturers themselves. They allow connections of sensor inputs and control outputs to microcontroller. When the board is powered on, the microcontroller with the loaded program will start executing the program. The capabilities of the microcontroller will be demonstrated using this board. This board will be fitted with switches, inputs, and display devices. Then next one is evaluation systems. So they are single board system with one microcontroller as the CPU and also as the control unit. These systems will come with an assembler software and a serial communication interface for connecting to a PC. Software is provided at the PC side in order to convert assembly language program to machine code and download the machine code to the memory provided in the evaluation systems. The evaluation system allows programmer to design and build projects of some lower level complexity. The evaluation board can also have internal flash memory or external RAM memory to accommodate all user programs. The next one is programmers. Programmers are required in order to dump machine language program from a storage device into the memory device. They are programmers that can load programs to flash memory or EEPROM memory. They are able to program a variety of devices starting from 8-pin to 16-pin device from the same family of microcontrollers. Next one is emulators. So they are used to develop advanced applications. They allow the execution and monitoring of software in small steps called single stepping mode, and it will also allow breaks in the program to test the sections of software at a time. Emulators can also have performance analyzers that indicates efficiency of the programs that is written and also suggest possible places that can be rewritten in order to improve on the efficiency. So the next device or the developing system are simulators. So simulators are software tools that are loaded on a PC. This will allow testing simple arithmetic manipulations and testing mathematical algorithms. Hardware is not required for a simulator, and hence it is a very safe mode for testing programmers, and especially for beginners it will be very helpful. The next one will be C compilers. So before we go for C compilers, let us see assemblers. Assemblers are software programs that converts assembly language program into machine level language programs. The next one is compiler. They are software programs that takes list of instructions. It is high level language program and converts them to machine level language program or machine code. Often compilers are embedded systems and are called cross compilers. They are provided by microcontroller or microprocessor manufacturers themselves. So third-party tools for conversions are also available and that can be made use of. And these compilers are specific to the families. So compilers, in addition to machine code, will also generate assembly language listings and it will supplementary files that will assist you in finding out memory locations and for many variables declared in the program. Is logic analyzer. So these logic analyzers are expensive tools and it is used to probe the state of the microprocessor or microcontroller pins. These tools will have a higher logic and it allow precise timing calculations between signals. So in this video, we studied the difference between microprocessor and microcontroller. We studied what is assembly language and how is what is the internal working of the computer, and we studied the different developing systems required for a computer.